Hello everyone, hopefully you're doing well. In this video, we're going to continue with chapter 3, numbers in the real world. If for some reasons you missed the first video, the first two videos covering this chapter, numbers in the real world, I strongly advise you to go back and watch the previous videos on the, we did 3.8 uses and abuses of percentages. Section B, B, putting numbers in perspective. In this video, we're going to take a look on dealing with uncertainty. So for those of you who don't we are not familiar with numbers or maybe use numbers lightly, like how much money you have in your pocket. We know we expect this number to be positive, not negative. You cannot say you have negative $20 in your pocket. The same way, for your age, the number of siblings, we expect those numbers to be whole numbers. That means you cannot say you have two and a half children, right? So that's very important when we deal with people. The US death, at some point, we make some good projections on the numbers. Like by 2000, they already project by 2020 that they were going to uh, raise or eliminate the US debt. But that was a projection over 20 years. But after 20 years, I think US still in a big debt, maybe over 30 trillions. But let's talk about numbers, dealing with uncertainty, what it really means. Suppose you measure your weight. Sorry about that. I'm gonna take a very simple example to explain. Suppose you measure your weight to be 132 pounds. Okay, so let's say that your weight is 132 pounds on a scale that can read only to the newest pound. Saying that you weigh 132.00 pounds, we would assume these two numbers are, may misleading because it would incorrectly imply that you know your way to the newest hundredths of a pound rather than to the newest pound. So, in other words, the measures of 132 pounds and 132.00 pounds do not mean the same thing. So that's what we're going to see in these sections. As we said, the digits you can see in a number that represent actual measurements are called significant digits. So those are the digits you feel like you're going to need, and those are very important. For example, as you see, 132 pounds has three significant digits, has one, two, and three, one, three, and two pounds. They are three significant digits, or and implies a measurement to the newest pound. While 132.00 pound has five significant digits, one, two, three, four, and five. Okay, that implies a measurement to the newest hundred of a pound. So note that zeros are significant when they represent actual measurements, but not when they serve only to locate the decimal point. So we assume that the zeros in 132.00 pounds are significant because there is no reason to imply them except to represent an actual measurement. In contrast, we assume that the zeros, you know, let's take another example, 600, for example, 600 centimeter, right? So if we use 600 centimeters, zeros in that not really significant because they serve only to tell us that this decimal points come to the right. So if we rewrite 600 now, instead of saying 600, do you agree it can be also 6 meter? 6 meters, 600 centimeter, or 6,000 millimeter, right? So the six makes it easier to see that only the six is significant, significant digit. So the only subtlety in counting significant digits arise when we cannot show whether zeros are truly significant, right? Now, you see, we have those types in these examples. Here, non-zero digits, we have type of digit and significance. Non-zero digits always significant. Zeros that follow a non-zero digits and lie to the right of the decimal points, like, if you do 4.20 or 4.00, 3.00, right? Those are always significant. But zeros between non-zero digits as like 4002 or 3.06 or other significant zeros such as the first zeros in 30.0, right? Those are also significant. I mean, you know, let's say for example, zeros to the left of first non-zero digit, those are never significant, you know. Well, actually, they are not really significant. Do not confuse when we take a big number and we are talking about significant digits. All right, it's two different things we need to cover. Zeros to the right of okay, zeros to the right of the last non-zero digit before the decimal points, like 40,000, right? Or if you do 210 or you do 520, right? Those are not significant unless states otherwise. So at some point we're gonna see it in the examples. Now, for these examples, the questions is they ask you state the number of significant digits and the implied precisions, of the following numbers. So we're gonna go over precisions very quick, but zeros, if for some reasons you forget how to do this, I'm going to use a different slide and explain, the decimal point. Let's suppose, okay, let's suppose we have a number like, we're gonna have a number like 4, 7, 6, 9, 3, 1, 7, 6, 8, 2, 1, 4, 5 dot. Remember, comma and dots, they are two different elements, right? When you deal with numbers. Let's go 6, 8, 7, 0, 3, 2, 5, 4, 4, right? Now, what you're gonna say here is, what these numbers are. Can you read this number, right? This example is very important to say. Like you said, on the left, you have uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Remember, for us, we read those numbers. If we have only three digits, we are in the hundreds. Six digits, we are in thousands. And above six, we are in millions, and whatever we have between from 9 to 11, so we are in billions, and after that, we are in trillions. So, if you remember how to say that, this one is what? Yes, it's a ones. Ones, and this one is tens, and this one is hundreds. No decimal, right? And this one is right now. After you go to hundreds, now we can hit thousands. So we are in the thousands. And it is, yes, 10,000. And six is, yes, 100,000. Now we done. I mean, if we write, I like to write 100,000. So you know what? Let me write it properly. 100,000. Now, after thousands, you go to millions. So is that for us? This one is millions, 10 millions, 100 millions. And now we done with hundreds, we done with thousands, we done with millions. How about if we go now with billions now? So by 9 digits, we hit billions. So billions, 10 billions. And for that one right here, it is 100 billions. All right. Now, after you're done with 100 billions, what do you have left? Yes, we're gonna have trillions. So this one right there is trillions, right? Trillions. All right. And then we can continue. But usually that's how we're gonna call those numbers when we round numbers, requiring that we call values on one side. So now this is what we're gonna do on the right, okay? So this example gives the place values that represent by numbers before and after the decimal point. So you see here, we're gonna go after the decimal point. How do you call the closest one to the decimal point? Do you remember this one? Yes, that the tenths. Well, we call this one tens. We don't have ones. We do tens, that's zeros. And you call this one, if you call this one, what you're gonna call this one, that's hundreds. And this one, you're going to call it what? The sevens is the thousands. And zero, how do you gonna call zero? Yes, zero in this case would be 10,000. I mean, there is a TH after each of them. 10,000 because it's in decimal. Now let's go with three. All right. So if you go with three, three is 100,000s. 100,000s. Remember, there is a TH at the end. Now, how do you call two? Two is millions. Like you do millions. And don't forget, you need to put THS. And five is what? Yes, five is 10 millions. And the first four is 100 millions. TH. And this one, billions. Billions. All right. So those are how you read these decimals. All right. So because I wanted to make sure after you understand the significant zeros, significant digits, but you also know the decimal point. If they ask you to read that number, we're talking about 4,769,317,680 2,145. That's how you're gonna read these numbers, and also you have all those digits in the decimals. So now you can do this. I think we're ready to move forward with our first examples. They said state the number of significant digits and the implied precision on the following numbers. If you take now A as an apple, so for A as an apple, 800,234, there are four significant digits. So because all these numbers are very important, there are four significant digits, right? All right. There are four significant digits, and it is precise to the newest one, right? Whole number. So it is precise to the newest one. So precise to the nearest one, right? So I'm gonna put it like this. Okay, it's a whole number. But if we go with B, all right, so for B, we said that how many digits we see here? Can you count them? It's one, two, three, four, and five. There are five significant digits. And the precision's about the precision, and it is precise to the nearest what? Focus on the decimal point. Precise to the nearest hundreds. Remember, hundreds is really something. Hundreds with THS. Okay, so very important. Now, look at C. What would you say C would be? Because for C, um, you know, we said that how many significant digits here? Only three. So one significant digit is three, right? Significant digit. Only three is the significant digit in this one, and it is precise to what? Newest thousand, because look, tens, hundred, thousand, tens, hundred, thousand, because we are in decimal. Precise to the nearest thousands with 8th. All right. Now, if you look at D, for D, sorry, significant digit for us, what would that be? Only three and five, right? So there are two significant digits in this one, and two significant digits because only two five significant. Those are zeros, It's all depends of the place of zeros. That's why we said if you still don't get it, strongly advise you to review that tables and understand when the zeros are significant. You see, 35,000 is like the last examples where we talked about 40,000, right? They are not significant, for these specific examples, we said there are two significant digits and it is precise to the newest. Just count this. 1, 10, 100, thousands, right? So, but it's gonna precise the newest 10,000s, right? Newest 10,000. Precise, yeah, newest 10,000. Yes, terribly terrible writing this, so sorry. 10,000s with DS only. All right. So this is one examples when we ask you, when we are asked to state the number of significant digits and the implied precisions of the following. So we try to show this here and explain why those numbers are very important. But also, we can verify if they ask you, carry out the number, the indicated operations, and give your answer with the specified number of significant digits. So here they give you a few examples. So in these examples, what they ask you to do, you need to carry out, uh, the the information. So now look at 386 times 43.2. Now, when you multiply this one, what they ask you to do is, they said only use five significant digits. So if you grab a calculator and you multiply these two numbers, let me grab a calculator very quick. I'm going to multiply. Give me 1 second. Grabbing a calculator. All right. So we said 346 times 386 times 43.2. All right. That's really give you five significant digits. So 1, 6, 6, 7, 5. It gives us 5.2. But because we're gonna do only significant digits, we're gonna keep we would keep only this part. Okay. We would keep only this part right there. Okay. Now you see it. How about the next one, B? Because for B, it would be exactly the same thing they ask you to do. 345 divide by 0.36. So if we do divisions out, 345 divided by 0.36. Okay, so this number actually give us something different. So it's gonna if we multiply, again, they said five significant digits. So we have a lot of digits, but we're gonna take only five of them. So when you multiply, it gives you 9, 5, 8.33. We have a lot of threes, but we're gonna take only 0.33. So that make it 5. All right. Now, if they ask you for the next one to you know find take only three significant digits, the first thing to do with C, C they ask you to do that. You need to multiply. Okay, you multiply 182 with 6.5. Okay, 1.82 times 6.5. All right. In this one, what we have, we're going to, the first answer, okay, first answer we find when we multiply 1.82 times 6.5, 11.83. But remember, when you do 10 power 3 times 10 power negative 2, same base, we're going to add the exponent. So that gives us only 10. Now, now look, if you have 11.83 times 10, that gives you 118.3. But now the goal is only to keep three digits, three significant digits. To keep two significant digits, what we do, we only take 1 point, okay? We're gonna take 1.18, okay? 10 power, if we make it 10 power 2, right? So we drop the 3 because the 3, otherwise we could, what we could do is round up, but there is nothing to round up. We take 1.18 times 10 power 2. Okay. Now that's our second examples, and hopefully you would use it to do more. Let's continue with these sections that cover dealing with uncertainty. We're going to talk about types of measure error. All right. So we are now ready to deal with errors themselves. We will begin by looking at two types of errors, right? Random errors and systematic errors. Then we will discuss how to qualify the size of errors and how to report final results to account errors, right? So the first thing you need to remember here, types of errors, we talked about random and systematic. So broadly speaking, measurement errors fall into two categories, as we said. You know, suppose you work in a pediatric clinic and use a digital scales to weigh babies, right? If you've ever worked with babies, you know that they usually don't lie quietly when put on a scale, right? The wiggling and kicking tends to shake the scales, making the wheelbarrow jump around. For the case, you could try it yourself. When you put it, it's gonna move a lot, right? That's very important. So we say that the shaking of the scales introduce a random error because any particular measurements may be either too high or too low when they shake. So we said random errors occurs because of random and inherently unpredictable events in the measurements process. Like when the babies shake a lot, you have the babies on the scale shaking, it's producing some errors. Now, this is random error. Now, suppose you have weight babies all day. At the end of the day, you notice that the scales read 1.2 pounds when there is nothing on it. If this problem was present all day, then every measurement you made was high by 1.2 pounds, right? This type of error is called systematic error because it is caused by an error in the measurement system. That is an error that consistently or systematically affect all measures. So that's why we call systematic errors. So this error is in the system. It's not your fault. It's not the fault of anyone's, but it's in the system. So we said that systematic errors occurs when there is a problem in the measurement system that affects all measurements in the same way, such as making them all too low or too high by the same amount. So it's very important to see that. Now, speaking about errors, we can also see size of errors. Size of error, like absolute errors, beside wanting to know whether an error is random or systematic, we often want also to know whether an error is big enough to be of concern or small enough to be unimportant. That's very important to say because the size of error, some errors are so big that you need to redo everything, but some errors are not really significant. Exactly when you place an order, if you find only one defective item out of 1,000, you said it's not significant. But if you find 200 items defective, from an order of 1,000, you would definitely return it. So what we want to do, I'm going to go with a different examples to illustrate. Suppose you go to the store and buy what you think is 6 pounds of hamburger, but because of this store scale is fully calibrated, you actually get only 4 pounds. So you are likely to be upset by this 2 pounds error. All right, that's right. Because you buy 6 pounds, now you realize they give you only 4 pounds because of a systematic error. Now, suppose you order 3,000 pounds of hamburger for a town barbecue, but you actually receive 2,998 pounds. So you are short by the same 2 pounds as before, but in this case, the error probably doesn't so important. So you see what we mean? Let me explain. We said that you buy 6 pounds of hamburger, and when you get home, you realize they give you only 2 pounds. You give you only 4 pounds. So you lost 2 pounds, right? So you're gonna be very upset because you bought for 6, now they give you for 4. Now, suppose you buy 3,000 pounds, but when you get home, you realize they give you only 2,998. So 2 pounds is the same 2 pounds out of 3,000, like the 2 pounds out of six, only six, they are totally different, right? So it's really different from what you see. All right. So that's why we call the size of errors is very important. So in more technical language, the 2 pounds is both cases is an absolute error. Of course, it's an absolute error. Okay. It describes how far the claim or measure's value lies from the true value, right? So eh, absolute error equal measured value minus true value. Okay, it can be positive or negative. Measured value minus true value. Okay, a relative errors compare the size, okay, of an absolute error to the true value. I think we covered a few things like this before. The relative error for the first cases is fairly large because the absolute errors of 2 pounds is half the true value of 4 pounds. Okay, we say that this relative error is 2 out of 4, for example, because the error is 2, and then the true value is 4, so that's make it 50%. In contrast, the relative error for the second case I just told you about 3,000, it's like 2 out of 2,998. That's only 0.067%. That's really not significant at all. So that's why we're going to use these two formulas to find absolute error and relative error. So we're gonna do it, and hopefully we can illustrate through examples. So in order, because we're gonna try to do all the examples at the same times. We're gonna do all the examples at the same times, but let's cover some other very important topics. The descriptions of results. Some results are very accurate. Two key features of any report value are its accuracy and its precision, right? How accurate something can be. Although these two terms are often used interchangeably in English, right? They are not the same thing. So accuracy and precision, so we are doing science, so we need to make sure we know what's these two. The goal of any measurement is to obtain a value that is as close as possible to the true value. So accuracy describes how closely a measurement approximates a true value. An accurate measure has a small relative error. So you're gonna try to be as close as possible to the true value. But precision describe the amount of detail in a measurement, right? For example, suppose a census says that the population of your town or your hometown is 72,000, if you have, let's write it there, if you have 70, I mean, population of your hometown is 72,453, people. But the true populations, remember, we said that this census says 72,000, all right? But uh, the true value is 90, census says this one. True value is 90,000, right? The census value of 72,453 is quite precise because it seems to tell us the exact count, but it is not very accurate because it is nearly 25% smaller than the actual population, right? So accuracy is usually defined by relative error rather than absolute error, right? So that's what we're gonna see in all the examples we're planning on doing. Remember, if you never take a census, you would understand like US, they do the census every 10 years. The last census in the US was conducted in April 2020. And so far, the actual population of the US is about 331,500,000 people living legally in the US. So we're gonna have to deal with this one. All right. So very quick, let's go with a few examples. What they ask you to do in this one right here. They said describe um possible sources of random errors in the following measurements. So what we're gonna do in these examples, we're going to describe the errors, right? A bird census in which watchers count the birds in a 10-acre preserve over a 1 day period. So, do you identify any random or systematic errors? So, if you forget random and systematic, random errors, we said, okay, of random and inherent unpredictable events, but systematic, that's not your fault. I took the babies, for example. I said, when you put the baby on the baby balance, and because of that, there might be some errors. But if it's systematic errors, so that's not your fault. Let's go with that examples three. A bird census in which watchers count the birds in a 10-acre preserve over a 1 day period. So what we're gonna do, say for this one, random errors may occur when birds are miscount, right? If you miscount them, so you said, I'm gonna go with A. Random error occurs when miscount, right? Because I'm doing one example and let you do that. And systematic errors may happen. This may happen. The same bird is counted more than once, right? So systematic error. This is random error. Systematic error occurs when same bird are counted more than once. All right, so that's an example, right? If you count them, if it leaves and then returns to the region, or a bird that enters the region is not seen, again, it's also a systematic error. You count the birds in the area, and then all of a sudden, some of them left. Then they disappear and they come back. So maybe you would count them twice, or maybe you would miscount. So that's the systematic errors is like when you count them twice. All right, miscount is a random error. That's a precise examples, but we can try as many. If B, for example, the amount of money that surveyed people say they donate to charity in the past year, or they just give you something like that. They don't say any. So random errors could occur when people make estimates because they don't recall the exact amount, right? So that's random errors. They say, how much money did you give to charity last year? Well, I believe I give 5,000. How much money did you give to church last month? Well, because I don't work, I think I give only $20. For the whole month, you give only $20. I mean, it's an estimate. So that's random error. But systematic errors could occur when people tend to report that they donate more money than they actually donate. So let's say you make a systematic error if you said, I gave $1,000 to the church last week, but you didn't. So that's a systematic error. All right. So you misreported the actual amount. So, and let's say we see, I'm going to just tell you, but you can, the annual incomes of 20, the annual incomes of 200 people obtained from their tax returns. All right. Those of you who filed tax recently or about to file tax, it all depends. The annual incomes of 200 people obtained from their tax return. Random errors could occur when taxpayers make honest mistake or when the income amounts are recorded incorrectly, right? So that's random errors. You make mistake that you don't even pay attention to, or when the income amounts are recorded incorrectly. But systematic error for 200 people's incomes in their tax return, systematic error could occur when dishonest taxpayers report income amounts that are lower than the true income values. We call that systematic error. So I'm hoping you can use these examples to do more. In the meantime, we're gonna go with another examples. This is what happened. They said a tax auditor reviewing a tax return looks for several kind of problems. Okay, so the tax auditor review the tax and try to identify problems that include mistakes made in entering or calculating numbers on the tax return and places where the taxpayer report income dishonestly. Discuss whether each problems involve random. All right, so let's say problem one. What's problem one? Problem one makes mistakes made in entering or calculating numbers in the tax return. Would you consider this one random error or systematic error? Yeah, that would be random error. All right? So because we said random error, uh, because the mistake may be too high or too low. So that's a problem. But let's say problem two. What's problem two is about? Problem two. Places where the taxpayer report income dishonestly. Yes, that's systematic error. Systematic error. We're gonna write error like this. Systematic error, because the taxpayer likely underreported his or her income. So that's systematic error. We're gonna go with the another examples very quick because this one covers the absolute and relative errors in the following situation. So again, we're gonna go with absolute and relative errors. So let's do some absolute. Remember here again, absolute error describes, we're gonna go with absolute error describes how far a measure or claim value lies from the true value. That means, remember, we said absolute error. You buy 6 pounds of of cheese. You buy 6 pounds of cheese. When you get home, you realize they give you only four. So a mistake of two, but there is a gap of 2 pounds. Of course, you're gonna be very upset. But if you buy for 8,000 pounds of cheese, you get home, you realize they give you only 7,998. The difference is only 2 pounds. So it's not the same, like, not the same percentage of loss when this happens. So that's why you go with absolute error and relative error. Absolute error is a number, relative error is a percentage. So we're gonna go over example 5 to illustrate. So example 5, they ask you to um, find the absolute and relative error. So we're gonna do that very quick. Absolute and relative error. Okay, let's go with A. Your true height is, I'm gonna say true height, 1.73. Okay, like 5 feet 8 inches, right? But a nurse in your doctor's office measures your a nurse in your doctor's office measures your weight, your height to be 176. So you agree here there is a mistake, right? So in this case, measured height is what? 1.76. Now, very easy for us to find the absolute error. So what is the absolute error? Absolute. Uh, Forgive. Remember, absolute error is what we said again about absolute error. It is measured error minus, this is it, measured error minus true value. True value, or measured value minus true value. So here, measured value for me would be 1.76. True value is 1.73. So what's the difference then for this one is 0.03 meter. This is the absolute, because they ask you, this is the absolute error. The absolute error is a number that can be either positive or negative. Now, relative error, let's measure the relative error. Relative error is, we can go with relative error. Uh, you know, relative error is, you know, we said in definitions of it, absolute error over true value. So we said absolute error, absolute error is 0.03 over true value. True value is 1.73. So what this one would be, okay? You want what this one would be? Uh, from using the calculator for this one, it is 0.017. That is 1.7%. So this is the relative error they make. You know what? I'm gonna try to do another one because so far I feel like doing another one would be great. We can choose any. You know what? Let's do Diaz and dog because I'm leaving you with most of them for you to do to review. I just show you how to do absolute and relative error. So D, you buy a sweat. Okay. So we're gonna go with D. You buy a sweater for $60.45, right? So sweater, $60, that's $60 and 45 cents. So that's a true amount, $60.45, including taxes. But your credit card statement shows a charge that's a measured amount. I'm gonna call it measured amount, right? It is 70.45. So you know absolute error in this case is the measured value 70.45 minus 60.45. All right. So we know at some point they make you pay an extra $10. I mean, they take an extra $10 from your account. So relative error is absolute error over, okay, relative error is absolute error over um, true amount. So 60.45. So what it is 0.165, 16.5%. Again, here, that's very, 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 very important to understand, okay? Hopefully you get it. Now, last sections to cover in this one is really talking about combinations. For us, combining numbers. I'm gonna explain using examples. So suppose you live in a city with a population of 400,000 people, right? If you live in a city with a population of 400,000 people, one day your best friend moves to your city to share your apartment, right? What is the population of your city now? Would you say 400,001, right? So you may be tempted to add your friends to the city's population, making the new population 400,001. However, the number of 400,000 has only one significant digit, you know, implying that the population is known only to the newest 100,000s, right? So it's 400,000. I don't know, even though you would want, but doesn't really make a big difference. The number of 400,001 has six significant digits because now, if you said, you know what, because my friend is at my house now, I no longer have 400,000 because here you only have one significant digit, which is 4. But here, six significant digit because now, based on the first slide we show you in this section, all right, it's gonna do it after you. So six significant digits, right? Um, yes. So the number, that's what we said. So clearly, you know, your friend's move cannot change the fact that the population is known only to the newest 100. So the population is still 400,000 despite the addition of your friends, right? So we must, of course, we must be careful when we combine measures numbers. Otherwise, we may state answers with more certainty than they deserve. In scientific or statistical work, researchers conduct careful analysis to determine how to combine numbers properly, right? Uh, so we're gonna do most purposes we can use two simple rounding rules. Uh, you know, Rounding rules for addition or subtraction. Round your answer to the same precisions as the least precise number in the problem, right? And also rounding rule for multiplication or divisions, round your answer to the same number of significant digits as the measures with the fewest significant digits, right? So to avoid errors, you should do the rounding only after completing all the operations, not doing intermediate steps. Okay, very important. Um, we're gonna see this very quick. All right. Okay. Now let's do this one. Um, Use the appropriate rounding rules. Okay, we're gonna do these last examples. Use the appropriate rounding rules to do the following calculation. Express the results with the correct precisions or correct numbers of significant digits. Okay, so that's exactly what we're planning on doing. Mhm. Add 0.6 pound to 136 pounds to find your weight before you went for a run. Okay. So what we're gonna do in this one, you have 136 pounds, and you're going to add zero point 0.6 to it. 0.6. What this one would be? That would be only 136.6 pounds. This should be round to the newest ones because that's the level of precisions, right? That's the level of precisions of 136 pounds. So the closer we can round up. So we're gonna make it 137 pounds, right? So this one is precise, right? We said this should be rounded to the newest 1 pound because that's the level of precision of 136 pounds. So that's why the final answer is 137 pounds, right? If you agree with that, and I'm fine with it too. If we go with B, all right, B, they said multiply 12 feet, cubic feet, all right? If we multiply 3 cubic feet by 64, no, 62, 62.4 pound over foot cube. Remember, it's very important to put it that way because, in multiplication, we can cancel these two. So what we have left, when we multiply 12 times 62.4 pound, final answer would be in pounds. So in this case, we got 748 pound, 748.8 pounds. Now, since 12, okay, since 12 has two significant digits, I mean only one and two, and 62.4 has three significant digits, we must use only two in the final answer. So that's why we need to decide what we're gonna do. What is the closest here? Well, you can go the closest like 100, 49 or, 740. We need to do only two significance. So do not do three because if I said 49 is it's gonna be the same. To make it, it's better we go with 750 pounds. In this case, we have only 7 and 5 as the significant digits. If I round up to 749, 749 make it three significant digits. If I leave it 748 is three significant digits. But because we need to round it with the digits like the first one, it is only 12, 1 and 2. Let's do another one and probably we can stop there for the day. Let's do F as in Frank, and I'll leave you with whatever you have left. What is the per capita cost of $2.8 million library in a city of 120,400? All right. So again, here what we're gonna do is, the per capita cost. What is the per capita cost? The per capita cost would be what? Yes, it's cost. Remember, it's the money divided by the population. So we have 2 millions, 200, 2.8 millions divided by the population. What is the population? 120,400. Mhm. So when we do the measurements, it gives us 23, 23 point, I mean, that would be in dollars. So let me put dollar sign first. $23 and 26 cents per person. So the per capita cost, we said that what is the per capita cost of $2.8 million library in a city? So that's been $23 and 26 cents per person. That's what uh, we see in this one. All right. Now, however, since the first measurement of 2.8 million has only two significant digits, remember that. So we have only two significant digits in 2.8 million. It's only 2.8, 28. But the second one, how many significant digits you think it has? Because 1204, that make it four significant digits. The answer must have only two significant digits. So we need to round this one down to only $23 per person. Okay. So that's what we're planning on doing. So I hope this one was very helpful for you to do any works you're planning on doing. So in the meantime, I'm gonna come back with some index, especially with CPI. Probably you heard about CPI, Consumer Price Index, in the next video. Take care. Have fun.